Tucker Platt is a mechanical engineer at Montana State University. The revolutionary design of the sub was almost entirely his responsibility. Tasks that he accomplished are everything.
Sam Hogue, an electrical engineer studying at Montana State, took on the sub challenge. He had to cover the electronics and the wiring systems, along with the interfaces.
Jonathan McGee, also at Montana State, in the computer engineering department, had the task of hardware and cameras and the website.
Alex Reed, a mechanical engineer, a lone wolf, had the responsibility of designing the end cap, the thinned end cap for dissipating heat, and also analyzing things with FEA. He enjoys going on long walks with his .44 pistol in unpopulated areas.
Jeff Witt, also a senior at Montana State University in computer engineering. I got to take the RoboSub, touch it with my magic wand, and endow it, this beautiful lump of plastic and metal, with life in the pool.
Matt Danzig, the Montana State University, mechanical engineer, responsible for many things.
David
Mantha.
He's an ME at Montana State University.
He likes tacos.
And he left too early.
So he's not with us right now.
But he still has lots of ideas.
He designed the pneumatics.
Hello. Welcome to the AUVSI RoboSub team. We're going to start with a mechanical overview, just a general overview of what we've been calling parts and the systems and subsystems that you might see here. First and foremost, we have a main pressure vessel. This houses the brain of the sub, a full Windows 7 platform, among other electronics, and pretty much all the electronics are in there. A 8020 or aluminum T-slot frame makes the bulk of the sub. That's all the blue stuff you see. Everything you see that's gold is an anodized aluminum part. So all the brackets, these end caps. These end caps were all hand machined here at the MSU machine shop. On the back here you see the feed through part of the cap. All of our wet connections coming through with a marine epoxy seal covered in silicone. Two switches you see here. The left one is for the computer, and the right one shuts the motors on and off because they're on two different circuits, and we'll explain more about that later.
Okay, we also have several components that are not as well. First we have a pneumatics chassis down below here. This is made of PVC pipe, Schedule 40, with a thin wall. You can also get it in a thicker wall, but we found that was too heavy.
Much too heavy.
We sealed this the same way with marine epoxy covered with silicone. We found that was our best and most reliable seal. And on this side, we used Teflon tape to ensure that nothing was seeping through these threads. Also here on the end of the pneumatics chassis, we have a bleeder valve, just so that we don't create a bomb. So to continue, we also have 6 C-Botics motors. We have 2 mounted vertically to move the sub up and down. We have 2 strafing motors and 2 more turning motors. So we have all but 2 degrees of freedom, and that maintains our stability. We also have designed this so that the center of buoyancy is right about here in the middle of the M, because this tube provides most of our buoyancy. And then down below where we have all of our heavy components and some weights as well, that's where the center of mass is, and that creates a riding moment to keep our sub stable in the water. We do have some supporting videos where you can see that in action in the pool. Also we have 2 torpedo tubes right here. They are pneumatically actuated and contain a guide rail for launching the torpedoes and directing the air.
The black plugs you see here were beaker plugs borrowed from the MSU chemistry department. So that's where you should get those because they're very cheap and very easy to use.
We also have 3D printed dropper tubes on the bottom here, mounted in the middle. This is our pneumatic regulator, and then our compressed air bottle is right here.
A little bit about the cameras. We have one horizontal camera. This is the GoPro you see on top. It's linked to the computer wirelessly, and it has to be above the polycarbonate tube with no metal in between it. Otherwise, it interrupts the signal. We'll get into more of that later. On the bottom, our vertical camera is a Logitech webcam, just a cheap one from the store. Just kind of just covered in epoxy. Maybe not a good way of doing it, but it is a way of doing it, and that's what we did. So
We also have some seals for the flange and the thinned end cap. This seal is also marine epoxy covered with silicone, and then this one is polyurethane seal. We also, on the inside of the electronics cap, the pass-through, we used polycarbonate, or polyurethane.
Polyurethane. It's important to note that when finding polyurethane, you want it to be as inviscid as possible, or the least viscous you can find, so that it can flow into all the cracks and then create a good seal. On the flange here, you'll see 8, I believe they are 3/4 inch long coarse thread studs with lock nuts in the back. And the inside of this flange has been tapped so that they actually screw in and won't slide when you're using the nuts here. These are good for alignment, and it makes things pretty simple when putting on the cap.
And now, just kind of as an overview of where we got all these materials, most of the materials we have here we got from McMaster Car, so McMaster.com. Ships pretty quickly, that was good. And everything else, like, we got most of our big, large raw materials from them, and then with the exception of things like the motor and this regulator, we got all that stuff from ACE.
Some other vendors we use for the anodizing process, we used 26 products in downtown Bozeman. They're really good to work with, really fast, really cheap, and you should use them if you want to use any anodized parts.
It was $70 to anodize everything.
The blue powder coating on this aluminum T-slot was done at Midwest Industries, which is also in Bozeman, just over the freeway on 7th Avenue. And they were also pretty cheap, relatively. It was $200 to do all of them, which is a decent price. Quick and good to work with, so also highly recommended. One thing we forgot to mention earlier is this white gum gasket in between. This is a modification from last year's use of O-rings. It creates a good seal as long as it's compressed evenly, which is what the stainless steel ring is for. The stainless steel ring was cut out of a flat sheet that was purchased at Pacific Steel in Belgrade and plasma cutted at the MSC machine shop.
The pig feet. These nylon runners on the bottom of the sub are affectionately known as the pig feet. They allow it to slide along without us having to lift it and carry it all over the place. And they're just basically sacrificial. We machined them out of self-lubricating nylon that we got from McMaster. And then we also have our lifting points here. We got these from ACE. And we have chains that we drape across here. Tucker's gonna get those. We can put those on pretty quickly and easily.
Using advanced clamp and hook technology.
We're gonna use these at the competition for the crane to lower it in. And we also have 2 of these so that we can put a spit through it and carry it like a stuffed pig.
So just one thing to note when using these, you don't want them to get locked up or jammed just in case they open. It would be pretty unfortunate to drop this from a distance. Because even though we try to design something that could be dropped from a small distance, still not recommended, obviously. We're going to discuss a little bit about the machining aspects on the mechanical side. Just in general, most of our, obviously the round parts were done on a rotary table on a mill. Holes, obviously just your basic drill press. All the brackets were cut by a vertical bandsaw, and all of the aluminum T-slot frame was cut with a bandsaw as well, with the exception of these specialized 45-degree parts, which were shaped on a mill. Dave is our resident machinist. I hope that you also have one. He's going to go into more detail about how some of the setup works.
So, the best way, if you're going to manually machine these, is to use the rotary table. You'll most likely be using, there's one especially large mill in the machine shop. So you'll have to be able to get that set aside for yourself during machining. The big thing with this is it takes time. It'll take, it took us lots and lots of time to machine it because we got to take
4 or 5 weeks.
Lots of time. Probably the best would be to try very early during the semester to get these parts into the CNC. However, if you can't, there are a couple things to note. When holding down this, you're going to want to cut out the outside first, because that'll get everything down to where you can start forming clamps. You'll want to clamp it right here and start milling the inside away. The rotary table will allow you to make everything perfectly round. This front part here, it was a press fit. The glue was more of just to hold it and make sure under pressure it'd seal. On the front here, we went ahead and machined fins to help cool. You don't want to make these too thin, otherwise they'll bend. So not much less than about 3/16. You'll want to anodize all the aluminum that you can. It's a lot harder than regular paint, and it wears a lot more. It's also not very conductive, so any shorts that form through it, it'll prevent that. With machining, aluminum doesn't need coolant as much, but you do need to watch that. It'll help just the labor of working it. So this part was on the rotary table. This was on the rotary table.
So, other parts that were made, these pig feet, those were milled on a vertical mill out of just nylon, really quick. You can bust out a few of those. The hope is that there won't be very much machining for you to accomplish. If there is, you get a lot of help down at the shop. A lot of the TAs, if they're still there from this year, will likely know exactly what we did and be able to give you some advice. But otherwise, we would recommend CNCing these parts unless you have about a month and a half to dedicate towards milling them. It was mentioned earlier that these parts are anodized at 26. They're good, they're fast, they're cheap. I would do that again. The blue powder coating was done at Midwest Industries, and I would also recommend them for their speed and relative cheapness. We're going to talk about the main seal of the main pressure vessel. First, we've got this gum gasket here, and it's mounted on 8 studs. These studs are screwed in to the flange, which has been tapped with threads, so they are permanently in there, and on the back you have a lock washer that keeps it from moving when wrenching it on the other side.
The bolts are 1/4 inch, just like everything else, just as a side note.
The gum gasket here has been treated with a silicone gasket grease. You don't need to go ape shit with the grease. You can just put a little bit on the middle and it'll be fine. So when you're putting this on, the switches are on the top. You're going to want to slide it in, line it up on the studs. And then
Now what's important to do here is make sure that you don't have any wires that are sticking out. Like if you zoom in right here, you can see we have a wire poking out, and that's going to compromise our seal. So
we'll try it again. When doing this, it's always good to have a person check what you're doing because it's really easy to forget to check for wires
there, that looks
or
good.
forget to screw down a nut. Now the stainless steel ring goes on the exact same way. There's a little M that stands for top, and that goes on the top, as you might assume. So this is also helpful. 2 people do. Hold it on. And then just bolts on like that. Stop. Start talking about the sockets.
tighten these nuts on, we're just using a socket. In the future, we may have a drill for you to use from ACE, which would be nice. But if not,
It's a, let's see, 7/16 size socket.
if not, we have a very rigorous spec for how much to tighten the gasket. You want 1/2 centimeter-ish of squish. That's about how much you want, all the way around.
And so when you're tightening these, you're going to want to go on a star pattern.
So we got that one already. Now we'll tighten this one, just like putting on a tire. Until we get the requisite amount of squish. Perfect.
Okay, now we should
There we go.
have a seal that, as far as we've tested, is good down to about 12 or 13 feet.
Yeah,
the
it's good
gasket,
12 feet, for
the
sure.
gasket seal is fine. It's the wet connect seals that are the bad ones.
We found that once we introduced dielectric grease, we weren't getting as much leaking inside the tube. And we know it's coming through these wet connects because we put a bag on the inside around that inner seal. So the gasket's good.
Another important thing is it's super easy to forget to tighten down one of these bolts, especially, or one of these nuts, especially if you're doing it by yourself. So it's always good to have someone kind of.
Yeah, so
Check on it.
after you do it, make sure that somebody goes around, somebody who didn't help, and just checks every bolt. Make sure they're at least hand tight.
And now you should be ready to put it in the water. The other thing that you might want to do is just every now and then put some more dielectric grease into the connections, because that seems to help.
If you haven't redesigned them already.
You should
Which you
redesign
should.
them.
I'm going to tell you a little bit about the pneumatic system. What we've done is just rotate the sub over on its side. And before we begin, you can just see here's the bottom facing camera and the bottom of the sacrificial pig feet. Don't worry too much about them, they're bulletproof. You can also see our droppers here, and I'll just show you real quick how we load the droppers. You just put it in from the top, and then you may have to push this little stud back over to lock them in place. We don't have a dropper here right now, but that's how you do that. Alright, so now I'm going to tell you a little bit about the pneumatic system. Now what I have here is the pneumatic CO2 bottle. You can get these at Bob Ward's, and you can fill them up for less than a 9 ounce. It's pretty cheap, it's like $3 or something usually. So the way that you prepare the pneumatic system is first by closing this interrupt. This will make sure that when you screw in the bottle, you aren't having any flow. So I'm just going to screw in the bottle here. Okay. Now, I'll make sure that this regulator is all the way turned out. You can see here, it's labeled for decreasing and increasing pressure. So I'm going to decrease it. Now I'm going to open the interrupt. So now our system is charged up to here, but it's only going to let out very little pressure right now. So then what I would probably do is rotate this back over, close this regulator, and watch our pressure indicator valve right here. So if this was a charged bottle, as I turn this, we would see a reaction from this gauge, and we would choose what we wanted. Alright, and now to take it down, after we're all done, pretty much do it in reverse. Reduce this pressure. Close the interrupt, and detach the bottle. Now you don't have any excess CO2, and you can bleed the system with any of the attachments you find laying around. We're going to tell you a little bit about how to remove the pneumatic system and show you how we do it. So to begin, I'm just going to remove this bolt right here, if possible. It's a terrible spot, really.
move this as well for easier access. It's pretty easy to do.
Now the reason that we want to take it off from here is because if we had loosened the hose clamp enough that we could just split it in half, it's possible that we could be cold working that strap back and forth, and it's only got a limited number of bends in it. It's like a paper clip, you know? And this takes longer, but at least it won't be as damaging. Alright, so you can see there we freed the strap. And now we're free to remove the chassis. Here, to get these connections out, it works like a shark fitting, if you guys have ever encountered those. So you can just grab it and push against the fitting and pull on the tube at the same time. And that'll release it.
Make a note about which connections go to which.
Oh.
So it's pretty easy. This
Yeah.
is, the center one is the hard wire, or the supply line. Having some troubles there.
Kind of, yeah. And that's all there is to it.
Like it.
That one's easier. This is torpedo. So just a note, you have to push in pretty firmly and then pull out. Pushing in on the fitting, just to be clear, and pulling on the tube. And this is the supply line, the last one that goes in the middle. Torpedoes will be the outermost fitting, and then the droppers are the lower ones. Now we need to disconnect our electrical lines. It doesn't actually matter in which order these are connected, because on the inside one is a ground and one is a hot.
So now, this part is kind of a bitch, but the Teflon tape seal makes it really stiff, so we've been using this clamp. It helps if you take off the pads here.
I don't know if you can take the pads off that one.
Okay, well,
With some of our other clamps, you can take the pads off and get a firmer grip.
we're just gonna go for it. This way.
Might have to get a better angle here. Got it?
We're gonna take off these pads. The pads have been removed, which should make this easier. Okay. Oh my lord.
The clamp broke.
Broke it.
You did break it.
Damn it. Okay.
A monkey wrench would be a smart investment.
Though it probably will break.
Probably.
Because we can't do it. Can't be done. Oh my lord, we got it. We're in business now. Sorry. Okay. Easy as pie. So inside of the pneumatic chassis, you will find a delightful nest, or web if you will, of electrical lines and pneumatic lines.
It's not actually unplugged in.
What's that?
It's not actually unplugged in.
Oh, it might have to.
That's good enough.
Okay. So the way this works is on the mechanical side, this is a hard line coming from the supply. These are always charged, and there are 4 solenoid valves in line with each other that can be fired at any time and with no specific order. Each one of these valves is rated for, I believe, 100 psi. What's that, Dave?
Yeah, they're rated for 100 psi.
Yeah. And the lines are also rated for 100 psi, aren't they?
They're rated for like 600.
600 psi. Okay, great. Yeah, so hard line, 4 solenoid valves can be fired without any specific order. The insides are attached just the exact same way as the outside tubes were, with the kind of push connect. With the wires here, we have one of these is a hot, and one of them is just a ground, so there shouldn't be any concern about the order or which side is connected to which.
So one of the wet connects is entirely hots, and one of the wet connects is entirely grounds. And you can switch them, doesn't it?
It's a little bit more difficult to see, but the wet connects were sealed with the same kind of marine epoxy and silicone technique that we found to be pretty useful. I think that's good.
I think so.
One thing to note is there is a Teflon tape around the threads here that makes it so difficult to open, but that also helps keep it helps constitute the seal. These valves are rated as splash proof, so they're not going to be destroyed if a little water gets on them. Obviously, it's still not a good idea to send them swimming, but it's not a huge concern. And on the outside of this is a relief valve that will relieve the pressure if there's an internal leak.
Without creating a bomb.
Without creating a bomb, yeah. It's actually a good thing if you see a little bit of bubbles coming out of the chassis. That means that the air on the inside is at a higher pressure than the water, so that helps to keep out leaks as well. Okay, so by far the most challenging and intricate part of this fine piece of machinery I'm holding are these clamps that open up. As you can see, that was pretty difficult. We'll do that again in case you can't follow it. So you're going to want to close them and then open them again. But good. Now you can have access to all of these wires and all this electrical stuff that I don't understand. That's the electronics chassis. So the way we made this is we had some 1/8" aluminum sheet that we cut into rectangles and then drilled a whole bunch of holes using a mill and a drill press. That's how we mounted all of the boards. I would tell you what size drill we used, but there were 2 different sizes and I have since forgotten. We just kind of guessed as far as size go. It was actually better if they were a little bit loose to give a little bit of leeway for the boards. Nothing too special, just cut some PVC pieces, that's this black plastic you see here, and then hand drilled them in. So nothing threaded, some pretty simple nut and bolt stuff.
So here are all your electronics board. This is an Arduino Omega ATX, what is it, 2560?
Yeah.
And then this is your solid state memory. We have 128 gigs in here. Solid state's the way to go. This is a homemade logic board, and on this board are 4 relays, 12 volt relays with 5 volt on off switches. And each of these controls the pneumatics. And it's good to note that on the far side, the inner pins, pins have been cut off, and the side with the outside pins cut off, and only the inside pins. That is your 5-volt switch, and the side with only the outside pins is your 12-volt relay side. And so that's good to know, and just a note for testing. This is the capacitor setup, which has three 3300 microfarad capacitors, totaling 9900 microfarads, because they're hooked in parallel. And that is what allows the computer to shut down properly after power has been disconnected from the power board. And then there's a resistor in there, which I think it's a 10K, but that's not too important. And then these are the motor controllers. There's 6 of them. Each motor controller has a USB, which goes to the underside to a USB hub and then back to the motherboard. But then there are 2 sets of wires here. One of them is an input from the battery, and the other is an output to the motors. And we'll get into that in just a minute. Then here we have the motherboard. On the motherboard, you have all your data and USB connections, which is pretty self-explanatory. Then you got your fan and your RAM. The RAM has lights, which is really helpful. But we'll get into the light description in a minute. And then your power board, and your power board has your 24-pin connector. And this is an M4 ATX power board. It's usually used in car audio systems, which is good because it's a really hefty power board. It has a lot of current, can source and sink a lot of current, and it doesn't have too much trouble with it. And also the light for this guy is right there that you want to be looking at when you're troubleshooting and just looking at that, but we'll get into the lights in a second as well. Also, there's a Wi-Fi dongle here, and the reason that it's placed here, it has just Velcro on the bottom. And it's placed here because the GoPro camera sits right on the outside of the chassis, right above it, and that makes for the best Wi-Fi connection because of the attenuation through water. Alright, so that pretty much does it for the front of the board and everything here. And now we'll go to the back of the board. This kind of looks like a mess, because it is, but it's actually pretty simple. What we've done here is we have 2 USB hubs. There's one here and one there. You could do one, but these are both smaller. They're 2.0 because all of our boards use 2.0. The only thing that could use a 3.0 is the camera. And since we don't have a need to hook that up this way, everything's just 2.0. Then these are power strips, and there's 2 batteries, and so we have 2 separate power strips accordingly. Off of the M4 ATX, you get connections that look like this, and off of this, there is a 5-volt power source, a 12-volt power source, and a ground. And so what we've done is we've hooked the 5-volt power source to here, we've hooked the 12-volt power source to these 3, and then we've hooked the battery straight to here. So you have a 5-volt power source, a 12-volt power source, and a battery level. And then for this whole power strip, the ground strip is from here to here. And that constitutes the electronics power strip. And so all the electronics are run off this. And by electronics, I mean basically the brain, the computer, and all the circuit boards that are on this layout here are all powered by that, except for the motor controllers. And the motor controllers are powered by a separate battery setup, and that goes through these 2. And that is simply just a battery level and a ground. And that goes to the power of the motor controllers. And then the other wires go from the power of the motor controllers out to a plug. Most of this stuff can also be found in the wiring diagram, and it's pretty simple. So now we'll go back and we'll talk about the technique I used, because if you're looking at this, you're probably freaking out because it looks like a mess. What I did simply was we talked to the MEs, and we did the clamshell so that you could have all your electronics on the outside of the board and all your wiring going to the center. And the reason we did that is because it's really nice to be able to troubleshoot with just the boards. And so some of the important things I did are pin out connections, simple things like this. If you look closely, it's just soldered to the pin, which doesn't seem to make a difference, but instead of wrapping wire, which they did last year, I always solder my connections, which make them look terrible, but they work fantastically. Another example of that is when we do the plugs here. As you can see, it just looks like a mess of electrical tape. But each one of these wires is twisted together, and then solder is applied to the twist in the wire, and that way this will never come undone and you won't ever lose your connection. And that makes it a lot easier because when something goes wrong, you're not looking for a loose connection, you're looking for actual problems with either the board or the voltage levels. And so just to go over what each of these is, this guy, I guess we'll go from the front, is your data cable connection. So what this guy has is your Ethernet cord and also a USB, and the USB is going to go out to the camera, and the Ethernet is going to go out to your Ethernet tether on the sub. And then this white connection is a USB extender for the Wi-Fi dongle, and then there are two USB connections here that go to the USB hubs. And the final USB connection, oh no, that one I already talked about. Alright, so that is one of the 24 pin output plugs, which not all 24 pins are used, but this is a male that goes to a female. And then this guy is a female plug, and you may notice that of the 3 plugs, there are 2 males and 1 female. And the reason I did that is because this female plug is a power plug. Power actually goes through this plug. It's not low level voltages and data, and so it's really dangerous to have the option of interconnecting it with something that has low level voltages or data, because you'll screw it up in a heartbeat. But so what this one has is it's got all of the engine outputs there, and those are pretty simple, plus on the top, negative on the bottom, and you can trace those back through the red and black wires to the motor controllers. Next to that, you have 2 battery hookups, and what happens is the battery comes in, and you have a positive from the battery coming in, and then it loops, that's why these are shorted, through a kill switch and then to ground, and that's what both of these are. So these 2 are going to be shorted because they go from the battery through that wire to a kill switch and then to what they're actually powering. And then the final thing you have is these 3 wires on the end here, 2 orange and a blue. Those go to the pressure sensor. 2 are going to be power and ground, and then the blue one is data, I believe. And so that's that. Let's see what's on this guy. Oh, this one is for all of your connections to the pneumatics. So this guy right here is a ground cord, and this guy comes from the relays on the homemade relay board, which is this guy. And so the yellows are the outputs. And so what happens with this is it's actually quite confusing, but once you get it down, it's pretty easy. You have your 5-volt inputs, and they turn on or off the relay, and those are from the Arduino. And so then these 5-volt inputs, when they turn on the power to the relay, all it does is short circuit this so that it makes a complete circuit. And then what you have is you have voltage 12 volts coming in from the battery, and it's hooked up to this side of the relay, and then when you complete the circuit, it goes through this side, and so then this side is hooked through the 4 outputs to each of the pneumatics control valves, and then back to ground. And so that's what these are. These are the 4 outputs to each of the control valves, and then 1 single ground, because you don't need to have 4 grounds. Let's see what else. Oh, other useful things. There is a reset button, which you'll find on the Arduino. That's helpful if your code starts going wacky. You just reset it and then re-upload the code. Yeah, I don't know what else to tell you. I guess I'll teach you how to troubleshoot now. All right, cool. Issues with the electronics that you may run into. Most of the issues that are not that are on the electronics boards and not outside components are I don't know, isolated through looking at the LED lights, but we'll get into that in a bit. But some of the issues that you won't run into is on these plugs, they're made pretty cheaply, so sometimes a wire and the plug will fall out. And to fix that, you just take a small screwdriver, which I don't have, but you go in there and you push it back in. And also, if you take these and you push them in farther to start, then they don't fall out. When they're made, they're kind of only put half in, and if you go in and individually push each one in, that's really good to have. Oh, it should also be noted that these are M4 ATX, which is our power board, but they're extenders, and that's what we made the plugs out of. So they're just 24-pin extensions, which means when you buy one extension, it's a whole line, and it's got a male on one side and a female on the other. You just cut it in the middle, and then you have a plug. So that's what we did for that. Other issues you might run into that we've run into with this guy are some of our relays went out. Those were easy to replace. You just cut them and put a new one in. And it's also, you just use a voltage DMM to tell what's wrong. And so how I go about troubleshooting is I start at the source, and I start with voltages and check voltage levels, and then I follow the continuity of the line and continue to check voltage levels all the way back to the source, and then after that I work on data. So for example, again, we had a problem with our relays, and so what we would do is first I trace the power of the relays back through the back side of the board and to the power strips, and made sure that they were all getting power with it on. And then after I figured out that they were all getting power, which while you're doing the power check, you can also do a continuity, because you'll know if something doesn't have power, then the line might not be continuous and you might not be getting source power. So power test, then continuity test, and then data test. And data test sounds pretty stupid, but with all the analog inputs that we have, it's really easy to just hook up your voltmeter and have your computer programmer or John or Jeff click a button, and then you can see if it varies quickly. And that's how you tell if you're getting good data or bad data, because we've also run into that problem with the Arduino. But again, a simple power check and data check usually solves all your problems, and you can isolate the source. One of the problems we had, again, was these plugs came out, and all I did was check if there was power. We had a problem with our pressure sensor, and all I did was check if the pressure sensor was getting power, and it wasn't. And so then I followed the lines back and figured out where the disconnect was and repowered it. So that's how I troubleshoot for electrical problems, which seems really simple, but if you don't get used to it that way, it gets pretty difficult and you just get frustrated all the time. So yeah, start at your object, check the power levels, then follow the object, like the pressure sensor, back to its source where the power is coming from, figure out if there's a disconnect, and if that doesn't work, then check your data. And if that doesn't work, then it's probably a bad board or a bad pressure sensor, which is your last resort. All right, so these are the batteries. What the hell is going on? That's probably what you're asking, because that's what I'd be asking. What we have is an extension to 2 batteries right here, and then 2 other batteries right here, and then a plug right here. And then after the plug, there is a voltage regulator for 24 to 12 volts. What it does is take anything over 12 volts between 12 and 24 and brings it down to 12 right here. Super neat, super neat. So this obviously gets switched out when you're charging the batteries. When you're charging the batteries, you plug this into another plug and then you charge it. Not too difficult. Wait till the green light comes on and then it's charged. This guy just plugs straight into the charger. These batteries are hooked in parallel because we don't want higher voltage, we want higher current for the engines. And this battery pack, which we call this whole thing one battery pack, powers the engines, and this battery pack powers the electronics. And the reason we have a 12-volt voltage regulator is because, as you saw on the board, we have to go through a power controller, and that usually reduces the voltage to 12. But since we're using 2 separate circuits, which is much more convenient, you have to reduce the battery level voltage back to 12 some other way, so we got a voltage regulator. Pretty simple, pretty easy, not too hard to deal with. So, we have our battery pack with an extension, and our other battery, and our voltage regulator. then our electronics board, pretty essential. You pop that in, just so it sits in. Slide the double battery pack over the top so that it falls into the back. And why we do that is because it evens out the weight so that you're more neutrally weighted and not awkwardly buoyant. Then you start to slide it in, and you got to make sure that no wires are over the top of the fan, because then the fan will rub on them and wear down the wires, and you don't want that. Then you slide it all the way in, and by all the way, I mean all the way, so that it's against the back and pretty much even. And if you look under here, you'll see that the batteries are just riding under the motor controllers, which is actually kind of important that they're just doing that. You don't want them to be too far, and you don't want them crushing the motor controllers because those are kind of expensive. Then what you do is you hook up all your plugs, and so 2 of the plugs protrude more than the others, and the female one does not. And so what you do is you take your power plug, which on this side is male and on this side is female. It's the only one that's male on the outside, female on the inside. Connect it simply like that. So see, this is one of the wiring issues that we're having. That just pops out. And it's a pain, and it can make things stop working, but all you do is you simply pop it back in, and then you take a screwdriver, and you make sure that it is pushed in solid. And then you look in the front and make sure that it's not awkwardly aligned or anything like that. Then plug her in, just like that. Then you look here, and this guy is, as you can see, it's got an 8-pin connection going to this wet connect, and 2 4-pin connections going to other wet connects. And so you know that's your data. 8-pin for Ethernet, 4-pin for 2 USB, although one of the USBs is not hooked up. So then you find your data over here, which is an 8-pin and a 4-pin and a 4-pin that's not hooked up. Connect those 2, and what that leaves you with is your pneumatics hookups, which is the final one. Hook that up. Now you're all hooked up except for your batteries. Now your batteries are these 2 guys. Now they are the same plug, which seems inconvenient, but as you see, one has tape around it and the other does not. The one with tape around it goes to your electronics. And so this one is just the single battery. So plug that up, let it hang for a minute, and then plug the other side of your voltage regulator into the other one, and now your sub has power, but is not powered on because your kill switches are still off. So now what we do is we take this guy and we set it simply right in the sub, and we take our voltage regulator and we set it right beside that guy, tuck the wires up, and then we take our electronics power, put it on the other side, and you want to put it under the wires if possible because, well, I'll tell you why in just a second. But so now the reason that you put it under is because when we place this on, it's a lot of wires, and you want to tuck it up top, because if you tuck it just in front, then most of the wires will fall out the edges, and then it's really hard to seal. But if you tuck it up top, it has room in here, and then it seals a lot better. So then you place this on like that, and then you put the ring on, like so. And then you simply put these back on, which we'll do real quick. One thing that you should note when you start this project is the wet connects. Right here are all of the engine wet connects, which, as you can see, ours are color coded, but last year's were also labeled and they weren't labeled well, so you may not like this labeling. So get familiar with it and do it yourself. There's also something to be noted here is that on these wet connects, I'll take off 2 so I can show you. They have a key that lies right here. That one doesn't have it either. Hang on. The point I'm getting at is that I cut off the key in some of them so that you can switch the engine orientation around. Yeah, that one has a key. Right on the bottom here, there's a little key so that it can only be oriented one direction in the plug, which is useful, but sometimes your engines aren't done right or wired wrong or just become a pain. So you can cut that off like I did in this guy. And after you cut it off, you can swap it. And this allows for your engines to be swapped so the direction of the engine can be swapped. So for example, one day we were hitting turn and it was strafing instead of turning. And so with that cut off, I can just flip the engine and then it turns when it's supposed to turn and strafes when it's supposed to strafe. And that's a lot easier than going into the programming because these engines can be run with both polarities and it just switches the direction, which is really nice. So now there's two switches here. The one to your right is your engine switch and the one to the left is the electronic switch. And since there's only one battery to the electronics, when you first power it on, it has to charge up the capacitors and the electronics board, and it can't do that all at the same time. And so now I'm going to show you how you turn it on safely. So keep in mind there's a switch here that I will be flipping. But what you want to do is put all your focus on that LED light that I showed you earlier. Alright, so this switch is finicky because there's a single battery and it has to charge up the capacitors before it starts the motherboard. And so what you're going to want to do is you're going to want to flip the switch on. And if it pays attention and listens, it'll do the blinky thing, then flip it off and back on real quick, and the motherboard will start. If it doesn't do that, just play with the switch, flipping it on and off in sequences of about like 1 or 2 seconds on, 1 or 2 seconds off, until you get the fast blinking light on your power board, in which, as soon as you get that, flip the switch right off and right back on. And then it'll start up. And so with that, we need to go into the LED light discussion. So these are the LED lights on your RAM. And this is basically an indicator that, hey, the motherboard's on, the computer's working, and we're accessing RAM, and we're doing good things. Those will go faster, as seen there, when your computer starts to access more RAM, and slower when it's accessing less RAM. They seem like overkill, but they're actually really useful indicators. The next light on the top of the board that's important is the green light that we just saw for powering on. This light is a solid green color when there's power being applied and it is on. When it's blinking slowly, that means that there's not enough voltage being applied to the power board. And when it's doing pause, quick beats, that means it's in startup mode, and that you also just witnessed. And so those are the indicators from that light. Those are the three that we've been using. The slow means not enough power or something's wrong. Quick beats, pause means it's starting up, and solid means that it's on. Next, on the bottom of the sub are the motor controllers. Those have two lights, which you see one is green and one is red. The green light is your data light. That means that data can be accessed to the motor controllers right now when it's green. When you actually send an input or an output, the green light will flicker quickly and then go back to a solid green state. The red light is the power light. That right now, when it's red, it's telling us that there is not enough or no power going to the motor controllers. When we flip on the switch, you'll see that it turns yellow. Solid yellow means that there is enough power to the motor controllers and that they can operate and give power to the engines and make them work. If it's blinking yellow, that means there's a power problem, but there's sufficient power. So for example, when we overpowered it, before we had the voltage regulator, if we're putting 18.5 volts to the motor controllers, instead of the 12 that they require, then you will get a blinking yellow light, meaning that it's got power, but in our case, it was too much power.
All right, now that the Blue November is all powered up and the computer has enough time to boot up Windows, we should be able to click down here and open the remote desktop connection. Blue November will be the PC right there, and just connect, and it should already have the password and connect straight in. Once here, you first want to click on RoboRealm, whose icon is this checkerboard down here, and this will open up our visual program. Once that's open, you can click on the icon of the gear, which opens the 3 windows for our RoboSub program. This chart will start tracking the depth of the sub once you click on the Set Surface PSI button. So now we have a blue line that will track the sub depth in feet. Don't really need that right now. This box right here is our console window, which provides information on what the sub is doing. It will tell you when it's performing different tasks, what file is trying to do those tasks, and what it's attempting to do. To run the sub manually, you'll want to click on the Enable button on the keyboard control, and then you want to stay on the dashboard window. If you leave the dashboard window, the keys won't respond anymore. But while you're here, you can use the arrow keys to run the lateral motors, forward, backwards, left turn, right turn. You can also use the comma and period keys for strafing. Depth control is done in the depth control section of the dashboard here. You set the target depth in feet, say 3 feet, and then set target. And you can hear the motors now trying to take it to that depth. Clicking the surface button will stop the vertical thrusters, and the sub should, due to the nature of its positive buoyancy, simply rise back to the surface. Okay, for autonomous operation, there is a mission planner here with a drop-down box of a bunch of the different separate missions in the competition. Most of these don't do much, but they all have some rudimentary development to them, so there's lots of opportunity to expand on what's already there. Right now we're going to go to the follow line mission, and by starting this mission, it should report to us in the console window what it's trying to do. So notice on the left, it's giving line mission, that's the name of the C# file, and then a colon, and then the action that it's trying to do from that file. Looking at the RoboRealm screen, we can see what the bottom camera can see right now, and it's kind of flashing around because it's picking up a bit of red color from the table. But if we give it a red object to look at, it should stabilize, and it will be able to track where that object is. The center of the object is shown with the yellow star, and the XY coordinates of that are being sent to the RoboRealm program, from the RoboRealm program to our RoboSub program, and that's how it's deciding whether to try and strafe left and right or turn, or if it loses it, to start over with the search pattern until it finds something that it can lock onto. You can stop the mission, and you'll see that it says mission stopped from the mission planner file, and it says line fail because it didn't complete by itself. And we can look through our cameras simply by clicking on the camera button down here. Now it's already depressed, so we're fine there. But if we want to change the camera, we can go to Options and select the camera here. Webcam is our bottom facing camera, and then the Minicam virtual webcam is our emulator that we run the GoPro stream through. So we can stay with the webcam. Now as long as the run button is unclicked, you'll be seeing raw streaming video. So if you move that object under there, you can see it move around. All of the filters that are used to process the raw video are implemented in order down here. So the first thing it does is scale it and kind of normalizes some of the colors. Then we use flood fill. Oops. Now notice that none of those actually take effect unless the run button is clicked. Once the run button is clicked, all of the filters will be applied in order. So first there's the scaling, and then a bit of color normalization, Flood fill will reduce the number of colors shown so that we can get larger swaths of the same color. Color filter will reduce it down to just a few select colors. The colors you want to select can be chosen by clicking Edit, and then right now it's only looking at this shade of red. One of the most useful things you can do is go to the filter right before the color filter and then click and take a color sample. Notice that it stays here, and then add that sample to the colors that the filter will detect. Click OK, and now the color filter will pick up the entire area with both of those colors. We then want to reduce all of this to just one blob so that we don't have any of these outlying pieces. And that's what the blob filter is for. We have the settings there set to just one blob. And then sometimes it can be more useful to replace the blob with a geometric shape so that it can understand, in this case for line tracking, what it's supposed to do. And then that displays our center point and the various variables being sent to the program.
Okay, so next we're going to show how to get the wireless GoPro action to work for the front camera. So first you have to depress the front button on the GoPro until you get the little beeps and the red light. So now we're on. Now you need to activate the Wi-Fi. So it helps just to turn it a little bit. And you depress the side button where the blue light comes on and just keep it held in until the blue light starts to blink. That means Wi-Fi is now on. There's also just a little tiny indicator right there, a little Wi-Fi signal so you know that it is working. So now this side is completely ready to go. We're gonna come back over to the computer. There's a little bit of a text document that we wrote outlining the steps, but I'll show you the actual steps. In this is a very important line. Copy that right now so you have it for later. I'm going to close that. So we're going to come down here to the Wi-Fi. You want to do this obviously when you're on the sub, so you're RDP'd to the sub. So you're going to look at your wireless networks and look for the GoPro forward. The other GoPro that we have is called GoPro down. Either one will work. They have the same passwords and stuff, so it doesn't really matter. So we're going to go ahead and connect to this. Wait a second for that to spin its wheels. Sometimes this can be a little bit finicky, especially when you're the sub's in the water, but usually running through the debug stuff Microsoft has built in will fix that problem. Nope. Okay, and sometimes it can say this and still work. So the way to check to see if it's actually working is you go into Chrome and you type in the IP address. And if it pulls up here, that means it's working. So even though it says it was unsuccessful, it's full of crap. So you're still good. Next step, you need to go into the VLC media player. Go to the media drop down and click on stream. From here, you go into the network tab. And this is where you paste in that URL that I had you copy from the text file earlier. It should be all over the documentation as it's a very important URL. So you shouldn't have any trouble finding it. Click stream, go ahead and click next. Then under the new destination, switch it to an HTTP and click add. Here you need to name it go.mjpg on port 8080 and then click next again. Up here you change the profile, it should be at the bottom to mjpg. Then click next and then that should be it. You click stream and see how this is flickering back and forth between play and pause. That's because it's playing the .mp4 file over and over and over again. That's just how GoPro works. It's a really kind of silly way to stream stuff, but it works, sort of. Anyway, so you want to make sure it does this. That means it's working. If it doesn't, sometimes the replay button's not depressed. Make sure it's on replay so it continuously loops that single file. So that's good right there. Then we're going to open up Minicam so we can virtually emulate this streaming, the GoPro stream as a webcam. So you're going to right click on the main window and go to IP cameras and click on the GoPro 1 and that should give you the stream of the GoPro. See, there's Jeff, it's working. You can also apply filters in Minicam and they will be passed through to RoboRealm. So right now I'm going to rotate the image so it shows face up since our camera is sideways. If you want to, if you want to change something within the GoPro settings, you can just go to Add Remove IP Camera, select the GoPro, and this shows you the URL for the stream that we're putting on through VLC. So it's just the local URL with the port 8080 and then the name you called the stream. That can be named whatever you want as long as it's .mjpeg, and then the name can be also whatever you want. So we're going to go ahead and close that. We don't need this window anymore, so just minimize that. And now you can go into RoboRealm. As you can see, we're still running the line tracking stuff, but now you can, actually I'm going to turn this filter off so you can see the actual switch. So we're looking at the bottom camera right now, and then when you switch to Minicam and click OK, now it's showing the GoPro. So then you can apply filters to this as you see fit. It's probably not going to pick up anything because there's not much red going on, but if we take the red screwdriver set, maybe we'll get it. Oh, it's just because it's looking outside, the lighting has changed. Maybe the buoy, yeah. Let me scroll down. Come on, click. Oh, yeah, we're sort of getting it. Yeah, the lighting is really weird in this room, but there it is. It's starting to show up a little bit. It's a lot more reliable when it's tuned for it. Plus, this is the line algorithm, and that's not supposed to be working on the front camera. So besides that, it works, and that's how you get the GoPro on the front to work.
So we've been running some filters that were left on due to the line tracking program being run, but sometimes we want to work with some of the other saved filter sets. So you can go to Open, and the buoy finder transdeck.robo file is the set of filters that's used for the buoy finding. So this way you can calibrate different color sets for your color filter and switch between them. And there we can start to see the buoy showing up just a little bit. There we go, with the star in there. And you can make changes to these color filters as I was showing before. And when you make those changes, you need to remember to save. So just save to the same file and replace it, and then those filter settings will be saved to that file. And that specific file will be the one that is called up by the C# programming. So let's go look in Visual Studio at some of the programming. There are two separate solutions, which is kind of the highest level of file groupings. There's the main solution and the dashboard solution. The dashboard solution is just the dashboard GUI, and the main solution contains everything else. So we'll go into the main. Within the main solution, there are a lot of subdirectories, such as main, mission planner, movement, vision, that handle different aspects of the programming. Be sure to look at the software block diagram and the documentation for some explanation on that. There should also be quite a bit of commenting on each line as to what it's doing, as well as at the top of the files. Most of the work you're going to want to do is on the missions themselves. So going into the mission planner, open the missions folder. In this case, we can go to the buoy program. So this is what's activated when you select the buoy mission. In here, things are handled using a lot of if statements and even some case statements. There's a state machine in each file that will run through different states, different scenarios for things that happen. So here, this first one handles going to depth. This one handles the search pattern, and once that's successful, it'll pass off to trying to center the buoy on the screen. Another important part is how I mentioned the RoboRealm files. Those can be selected in one of the configuration files, which is a little more obscure. So it's in main, config folder, and then the vision config XML file. And this is where you can set which file you want RoboRealm to pull up with the filters for any given mission that you're working on. So right now we're working with the gate, the line tracking, the buoy, and the parking missions. So if you forget to go into RoboRealm and just go straight into the subprogram, notice in the console there will be a bright red message with error and some exclamation points. This is the format that I decided to use to point out error messages so that we know where they are. Notice it still has the name of the file generating the error with a colon at the start, so you can find that file. And in this case, it tells you that in order to solve this, you need to have RoboRealm running first. So you want to exit the subprogram and make sure RoboRealm is running first. Another issue that might happen if you lose contact with the sub, or there is an error that simply causes the program to freeze, then when you exit the RoboSub program, RoboRealm might also get frozen as well. And if RoboRealm's frozen, you just need to exit and re-enter it. The biggest symptom of RoboRealm having issues with the RoboSub program freezing is that when you try and go to the color filters, you won't be able to take a sample as we did before. So here you can see that it's working because the colors are changing in this box. But if you can't take a sample kind of on the fly while you're working with the sub and the pool, just quit both programs and start over.
And then also along the lines of troubleshooting things, VLC, as powerful of a program as it is, does have its problems. So if it does by chance stop responding, you're going to have to cancel it, obviously, get out of it, open it, and redo all of the steps previously outlined again. Hopefully it doesn't happen too many times, but we've had a few different instances where it has crashed on us. So just be aware of that, and after maybe 1 or 2 times, it will eventually start working.
So now you've seen this awesome sub, you're probably like, well, what can we do? Because it's done so good. Not really. We're about to tell you what you're going to be doing for the next year, or our suggestion of what you should do. So the first thing that we'll talk about is, I think, the end cap design.
All right.
Or do you want to wait?
Yeah, we'll talk about it.
All right, cool. So this end cap is great, but there are a couple things that you need to know about it. The first thing is the wet connects. The company that you want to go with the wet connects is Seacon, S-E-A-C-O-N, and those files of the type of wet connects that you want, you'll find in our paper, which is really long, but just scroll through the paper until you see those documents. They're like probably 2/3 of the way down. And you're going to want to get on those first semester, start talking to Seacon, start ordering the wet connects, get a quote, and get those done first semester because those take forever to get in. And so there's that. And then
So with this end cap, we had to incorporate this reinforcement ring here, and we already discussed kind of why that was, but just a little further, we optimized this. We did an FEA analysis actually to make it as thin as possible. so that we transfer more heat and, you know, cut down on weight. But when we use bolts to tighten it, it kind of warped around and it created voids with this gasket. So what we're going to suggest that you do is mill a part that is just one piece out of some kind of aluminum plate, and maybe mill this center part down and leave a little ridge here for stiffness. And then you can just get longer studs and clamp it down, but it'll be lighter and more convenient than having this giant stainless steel kind of ugly thing here going on. And what we will do is actually provide you with a file, and if you guys feel like using it, you can. That it's going to be a step file you can open with Creo or SolidWorks, and if you want, you can just hand that right away to the
CNC guys.
yeah, the CNC machine, and they'll just, I mean, make it for you. Just hand it to them as early as possible, and they'll do it for you. It'll probably look something like this. We haven't quite made it yet, but we're going to do it in like 5 minutes. Now, we got just something like that. This is a little bit raised up here, and then you just have this lip for stiffness, and you'll have some holes going on here, you know, just like the old one. But this will still be thin, and you'll get the stiffness out of this, just one piece.
We don't have one for the other end cap, do we?
No.
Okay. The other direction you can go with this is you can design a whole new tube. You're going to use the same size tubing, same tube parts, same epoxies on both ends that they've used. And you'd have to redo this end cap, but the way that you would do that is you would have this end cap, same tube, but for this end cap, we've gone through all the possibilities, and if you don't do what Alex is talking about, the other part that you can do, the other way you could design the end cap is you could have the tube coming out like this, and then you have some sort of aluminum housing on the end of the tube that raises up and goes for about this long. And then, on top of that, you put in O-rings, 2 or 3 O-rings that go all the way around the outer diameter of the tube, like that. And so front view, it kind of looks like you've got your carbonate tube, and you've got your aluminum housing, and then you've got your O-rings that go around the aluminum housing and hold that tight. And that way, the O-rings don't fall off of the end cap, and they stay tight. And then what you would do is you mill another piece of aluminum that goes over this with a low tolerance, and your wet connects come out here. And then you can just slide the end cap over the O-rings and pull it off, and it seals. Then you just have a fixture back here so that it doesn't slide off, like a set screw of some sort. So those are the 2 directions that you're going to want to go with the end cap. Everything else just turns into mush and crap, and you don't want to go any other way. But that gives you some freedom with that, and it also allows you to do the entire new tube if you want to go that route.
So we would suggest that instead of having the batteries on the inside, that kind of ended up as a little bit of a mistake on our part. We just forgot to pull one of these leads through. So when you redo this cap, however you do it, if you do it, which we recommend again, you should pull the plugs out here, and then what we saw the past RoboSub team do, which we thought was pretty cool and useful, is cast these in polyurethane and then have a wet connect coming out at the top of it. So it was just a block with a little wet connect out here, and they had a little tray on the side that these could just sit in. However you guys want to attach these on the outside, that would provide more buoyancy and would be easier to unplug them, you know, switch them out, put them back in without having to undo all these bolts again. That'd be a quick fix and pretty significant.
And they're easier to charge that way.
Also, you're only going to have limited time during the competition too, so anything you can do to speed stuff up is great.
Let's see. Okay, electrical. These plugs are great but if you go with a new end cap, they're kind of just a quick fix because they're the M4 ATX extenders. On the inside, those 24-pin plugs, if you found a better specified plug, one that's more reliable, the ends don't fall out, and they hook up better, that would be something that you could also change for electrical, because that's going to make your life a little bit easier. Sometimes they fall out and they have problems there. So if you redo those plugs, that's good. Also, with electrical and programming, it would be nice to add in the IMU. That would be another thing. So plugs and IMU. Make sure you keep all your diagrams up to date. Also, yeah, I guess we had a problem with the GoPro cameras, but it's something to look into. You'd have to go into the firmware and change it. That would be a pain. That's the hard route. If you wanted to do 2 GoPro cameras, you'd have to go into the firmware and change the GoPros, IP addresses, and figure that out, which you would want to get on immediately because we have the GoPros. The other thing you could do is just go with webcams, but if you do that, you need a solid system, mechanical and electrical, to seal them off, to make them look good, and to make them work. And you also have to choose your webcams so that they have no contrast change. A lot of the webcams have an auto contrast, which is cute and great if you're using it as a webcam, but underwater all your contrasts change because of reflections and refractions, and that'll just ruin your programming and make your life miserable. So if you start off early, first semester, with webcams, then you can pool test them and check them and make sure you get a good webcam and it works good before you decide to use it. And getting a head start on that would be good. And then you want to talk about pressurizing too?
Yeah.
That'd be great.
So another idea we had that didn't quite come to fruition is we were thinking about milling another hole down here in the end cap, and then incorporating a bicycle pump valve or something of that sort, where we can pressurize the inside here, and then that way we can that'll help water not to get in, first of all, and second of all, we can hear or see any leaks before water gets in and destroys our $6,000 electronics here. So that's something that would be pretty good to include, we think, but it's up to you in the end. We want to talk about the torpedoes a little bit.
Yeah. So, there are a few of the torpedoes and droppers here. We wouldn't suggest making any changes to the droppers. This is last year's design, and it works pretty well, especially with the system they're set up now. So, if you wish to change that, you're free to do so, obviously, but it works pretty well. This is last year's competition torpedo. It's a 3D printed part by the people at Keyport. We don't have this nice blue material, and it works pretty well. These are ones I've set for some of the design changes we made this year. Is we've added some self-rifling fins, which keeps the torpedo spinning and stable underwater. Some things that you might want to do, well, some things that we still plan on doing is changing these fins so the angle is a little bit less aggressive, so the torpedo travels farther underwater and faster, but still spins and still stays stable. And we also plan on printing this at the or with the Keyport printer, so we can get this material, which is a lot less brittle. You can kind of see how the fins have cracked off.
Yeah, and this is more neutrally buoyant material as well. So it's just pretty much all around better. But I mean, also you might have some difficulty even getting these 3D printed here. I don't know what the deal is, but you've been a little stingy.
It's true. We actually had these printed off for one of our classes that allowed us to print independently of capstone, so we just kind of got lucky. You might have to talk to, oh no, Evan Kosker won't be here anymore. I don't know who's going to be doing the 3D printed stuff.
That's up to you.
That'll be an adventure of its sort.
Epic proportions.
Yeah.
Alright, yeah. I think that's about it. So, just again, an overview. First semester, what you're going to want to do is get familiar with this sub, go through all the stuff that we've already shown you, take it to the pool once a week, throw it in, play around with it, test it, make sure there's no leaks, make sure you know what you're doing, DMM test everything, bless you, and just get all that stuff under control. That's big. The second thing you're going to want to do is wet connects. That's huge. Wet connects need to be got on immediately. You have the CCON file. Look at these wet connects. The only other wet connects you'll need to add are batteries. Otherwise, you can know your pin numbers and what kind of wet connects and where to get them. But get on CCON early, otherwise you won't get them. So that's first semester. Let's see what else. Also, you're going to want to start looking into the cameras first semester because these take time. The reason we're telling you all of this stuff basically is because the difference between this class and the rest of your classes is it's an event-based system. So you can't continue with the cameras until they've been ordered. You can't order the cameras until you know what you're looking for. So you start with certain cameras, order them, check them out. If they're not good, order some other ones. And that's why you want to get on it immediately. Same with the wet connects. If you get on it first semester, you order the wet connects, get them coming, check them. If they're not good, order again. But it's an event-based time checking system. So you're ordering something, you're waiting for it to come, and then you're checking it. And same with the ME side. You're gluing something, you're waiting for it to dry, then you're checking it. But it's weeks at a time that you have to wait. And that waiting factor makes it so you can't just sit down for a night and just get it all done. So it's really frustrating. Yeah, go ahead.
Yeah, just a note about what Sam just touched on with the testing for leaks. We can almost promise you you'll be spending at least a couple weeks, or we even spent close to a month trying to fix our leaks. So it would be really beneficial if you could get on that early as well. And just a note about the pool testing itself. At least this year, we were able to go in at least once a week. Towards the end, every day of the week even. Usually the pool opens up at 8, I think, and closes at 9:30, and they're pretty strict about that closing time now. And
You're welcome.
we would suggest making the most out of it. Maybe even keeping a backpack up in the design lab with all the stuff you need, so that you don't have to get organized.
Yeah.
And watch out for parking tickets as well.
Yeah, definitely. Again, with that, another thing you should do is keep the sub running. So if you're going to change something electronically or mechanically, try to keep it running, So if I were to change the plugs, I wouldn't just take out the plugs right now and wait 2 weeks for them to come in. I'd order them, wait till they got here, and then sit down for a night and get it done and make sure it's all working so that the water test and the working sub isn't dependent on me. That's really important because you want to keep this thing going and working. Then, let's see, what else do we have? Go ahead.
One thing that we were going for somewhat this year but never really accomplished was setting up a RoboSub club.
Oh, yeah.
It would be really good, and we actually did get in contact with the robotics club here at MSU, but something that would be really great would be if you guys could start up a RoboSub club, find a sponsor willing to help you out, and then get the underclassmen involved, get them excited, get them working on older renditions of the sub, and see if you can't create a AUVSI RoboSub culture here at MSU. That way, hopefully, the people working on the capstone project don't have to watch this video
Over and over.
and over again to learn about the sub. And ideally, they've known about it since freshman year, and they're really excited to get to work. So that's something that we would like to see.
Also, if you could find a way to put in just a simple screen readout on the motherboard and or the Arduino, you could have that running so that when you're not tethered, you know what the sub's doing. That would be useful in lab and in the water. Yeah, so I think that's pretty much it. Again, first semester, you're going to want to get on those cameras, those wet connects. You're going to want to do all that research, IMU research. If you plan to buy a new IMU, do it. If you're going to use the one we have, fine, get to know it. So, yeah, first semester, wet connects, IMU, cameras. And start buying stuff. I mean, don't be afraid. You're not going to have to replace all the internal electronics, so you'll have a pretty big budget. So don't be afraid to buy something, test it, say it doesn't work, send it back. Just get on that quick. And then with the mechanical side, you're going to want to be looking at the end cap first semester, the wet connects as well, and then all the other stuff they discussed. You just got to get in and get familiar and just keep that going. And then also, Hopefully we did a good job documentation this year. Keep that going as well. Documentation is pretty important, so you want to really be focused on that. And yeah, I think that's pretty much it. It doesn't seem like a lot, but if you're working with cameras and IMU, that's going to keep your electronics pretty busy for 2 semesters. Doesn't seem like it, but I mean, if John had known about the GoPro IPs last semester, our camera setup would be twice as good as it is right now. But because he didn't know about it until 2 months before the semester ended, it kind of screws you. So definitely get on that and get started. With respect to the programming, just continue trying to program, keep the tasks going. If you get the IMU first semester, which you should, that'll be redundancy, but redundancy is really good in the system because it allows it to check itself. So then you're going to implement that alongside with the other programming, and that'll be really useful as well. And you want to get on that because again, waiting for any of this stuff sucks because it's all time based. And I'm pretty sure that should keep you busy for the year.
I'd like to talk a little bit about the budget and how you might be ordering parts. This is something that for some reason wasn't told to us right away, but there's no kind of 10,000 for MEs and 10,000 for EEs for the budget. Our budget this year was 20,000. That might change, but typically they like you to buy all the parts from the electrical department, and so you're gonna want to go through Brent in the stock room and Muriel upstairs. That's if you get something from Ace, you should make sure you bring the invoice and get it to her as fast as possible.
We recommend taking a picture of it as soon as you get it, and then just bring it straight to Muriel so you don't lose it.
And then as far as the ME side, they typically in the past have taken care of all the travel costs. It's perfectly okay if you spend more than $10,000 and have to buy parts on the ME department's budget, but they usually like you to take care of travel costs with that. So make sure when you're planning out your design, you leave about $7,000 or $8,000 for travel on the ME side.
And that's the other reason that we can't stress it enough. It's time-based. You have to order everything through Brent. Otherwise, you're almost paying for it yourself because it takes forever to get your money back, and it's kind of sketchy that way. So you're going to be ordering it, so it's 3-4 days for it to come in and all that. So definitely get on this stuff early. Most of the research on this thing is done for you. But yeah, otherwise, good luck. And if you need anything, try to email us. Hopefully we'll answer. But we'll see. We'll leave you a document with our emails on it too.
And hopefully we'll be able to give you a little bit of an update somehow on how the competition goes, so you can know what you need to fine tune,
Yeah.
what you need to make stable.
Yeah. But yeah, basically the difference between this project and all the other design projects is instead of designing the first semester and fabricating the second semester, you should now be fabricating the first semester and testing the second semester and fixing everything that doesn't work, because otherwise you're just going to be SOL.
Cool. Well, I think that covers just about everything, so good luck and have fun with it. It's a cool project.
Yeah, it's a lot of fun, especially when you get in the water. We've had some great times pool testing.
Don't forget to beat the Russians.
And
In
Cornell.
November.
And Cornell too, yeah.
And yeah, if you could take down Cornell, we would be proud.
I'd be so proud of you.
We might even come back and high five you.
I'll probably watch the competition.
Yeah, that'd be
Whenever
kinda
there's
cool.
a chance of beating Cornell.
Yeah.
Alright, we'll be watching.
But yeah, so wait, step back for a second. That's all the stuff you want. Hopefully you can see all that. Get on it.